What do waves do at boundaries? Basic answer is they reflect. I said under reflection that waves reflect off of certain boundaries, but it may have been more correct to say that really waves, to a degree, reflect off of all boundaries. It just that doesn't maybe make as much sense for a macroscopic point of view, but from a mathematical point of view, it turns out it makes a little bit more sense. Let's see what the information in this example is, since it is an informational example, and the answer says they reflect, but there are some different possibilities. So here's an example of a wave pulse on a string that is moving to the right, and then the string is tied to a rigid wall. And in that case, the reflection that occurs is the wave pulse comes back as a downward pulse. One way to think about this is Newton's third law. When the wave pulse encounters a rigid wall, it applies a force to it, and then it's the reaction force that actually creates the downward pulse. This second situation is where the string is connected to a frictionless loop that is allowed to move on like a pole or some rod or something like that that's fixed in space. And in that case, since there's no force really applied, since it's frictionless, the wave winds up reflecting in an upright fashion. Now, these are two situations. The first one is relatively easy to reproduce in the lab. This second one is very difficult, if not, dare I say, impossible to reproduce in the lab to get this to work perfect. But they are situations that relate to what is a little bit more realistic, which is when there is a boundary that is not quite maybe as rigid as these two boundaries are, in the sense that there's no medium on the other side, right? The wave has to reflect entirely here. But what is more within the bounds of reality is what happens when a wave is in a medium, then all of a sudden there's a boundary between that and another medium, and the wave can propagate into the new medium. What will happen? Well, in general, there will be a reflection. Some of the energy of the wave pulse will be reflected back, and some will continue. And in this picture that I've got my kind of hand-shaped cursor on right now, this is where we're seeing a wave pulse in a thinner medium going to a thicker medium, which a way of interpreting what that means is this is a medium where the wave speed is faster, and the thicker medium has more inertia in it, and so the wave speed is slower there. And it turns out that holds true for waves on a string, what I described there, but it can be applied by analogy to other situations. And this is analogous to the rigid wall reflection. So the reflected wave pulse winds up reflecting down. The transmitted wave pulse represents the amount of energy that still continues. The last case down here is a thicker medium going to a thinner medium. The reflection happens as well, but this is analogous to the frictionless loop. So here the reflected wave remains upright. The transmitted wave is upright in both cases. Now, this picture for these two situations, it winds up being really useful in optics. So there's a lot of optical kinds of situations where light can go from one medium to another, but in general, there's always going to be a partial reflection. And knowing whether that partial reflection will lead to inversion of the wave or not winds up being important to explain and understand, as well as predict phenomena. And when I say predict, that includes a wide range of applications, including things like reflection preventing coats on things like glasses.